In this video, we're going to learn how to conduct two different hypothesis tests. In particular, we're going to look at how to perform the one sample proportion z-test, as well as the chi-square test for independence. And just like previous videos, we're going to be doing this using the BRFSS so that you can use these different hypothesis tests in your reports. So to get started here, a couple files that you'll want to have. Of course, you'll want to have, if you're following along with the video, the data set for Kentucky. If you're working on the data set for your report, you'll want to have the data set for your particular state. Also open, I have the software assignment, so I can reference that. We have the R script that goes along the video, and then there's also an R script for you to fill out. Just realized I need to change that header, so I'm going to go ahead and do that right now. It'll be updated on Canvas for you. All right, so we're going to start out by first reading in that data set that we created back in Module 5. Again, I'm going to be reading in the Kentucky data set. You'll either want to read in the Kentucky data set to follow along or read in the data set for your state. So I'm going to start out by setting my working directory. As a reminder, this just tells R where on my computer the different files are. I'm going to read in the Kentucky data set. And then it's always a good idea to do just a couple checks on the data to make sure things look good. I know for this particular data set, I expect to see 2,869 observations with 18 different variables. And then I can either click here to open up the data set, or I can run this line of code where I've got View Kentucky Data to also view the data set. And then as usual, I just want to kind of scroll through and make sure nothing looks unusual, and this looks like it has in the past. So I feel assured that the data set read incorrectly. Now the next thing we're going to do is perform a one sample z-test. So before we get into the code, let's look at the assignment and actually talk about what it is that we want to accomplish with this one sample proportion z-test. So looking here at the assignment, we're going to be here in step 2, which is to perform a hypothesis test. And in particular, we're looking at the one sample proportion z-test. So what we're going to do in this section is you're going to look at your two topic variables that you have. And in particular, we're interested in compliance of that topic variable. So for example, you might be interested in the percentage of people that said they've had a mammogram, or the percentage of people that have had their flu vaccine. And then what we're going to do is we're going to do a one sample proportion z-test to compare what you found in your sample to a national statistic. And so here down below, for each of the different topic variables in the course, I have found a national statistic for those particular variables. But if in your report you already found a national statistic, please use those instead. And so when creating the infographic for your report, for example, you may have already compared some of your topic variables to a national statistic. And if you did, please use that value instead. All right, so we're going to go to the code, and as we work through the code, we'll talk about what this one sample proportion z-test is actually doing for us. So the first thing I'm going to do is I am going to load the tidyverse. Some of the code that we're using today will need the tidyverse, so make sure to go ahead and run that. Everything down there looks fine. I remember you will get a couple conflicts, but that's nothing to worry about. So I'm going to work with the pneumonia vaccine variable that we've looked at previously in these videos. So the very first thing I want to do for the pneumonia vaccine variable is give it some meaningful labels. And if you'll recall previously, when we looked at the code book for this particular variable, it takes 3 different values, 1, 2, and 9, and these represent yes, no's, and unknowns. So I'm just going to run this line of code, and again, we've seen this before, to create that new pneumonia variable that instead of having the numeric labels, will actually have the labels in words. And then the next thing I'm going to do is actually rerun the code from last week when we created that table that had both our frequencies, our proportions, as well as our confidence intervals. And so here is that table down below. So let's talk a little bit about this table and what we're seeing in this sample from the state of Kentucky. So in this particular sample, we see that there were 611 people who had gotten the pneumonia vaccine. And if you'll recall, for the BRFSS, in the pneumonia vaccine, this is restricted to adults aged 65 years or older. And so of that sample, we found that about 63.7% had actually received the pneumonia vaccine. And then we found a confidence interval where what that confidence interval does is it gives us a range of reasonable values for what's actually happening in the population based off of our sample. So based off of our sample, we estimate that between 60.6% up to 66.8% of the population receive their vaccine. And again, this is with 95% confidence because we create 95% confidence intervals. Now, what a one proportion z-test does for us is instead of creating a confidence interval, it allows us to ask a question about what's happening in the population. And so if we go back to the assignment here looking at the pneumonia vaccine, I've got a citation here, or not a citation, but rather a link from the CDC that says coverage among adults aged 65 years or older was 67.5%, which was similar to the estimate for 2019. So a national estimate for what's happening in terms of pneumonia vaccine is about 67.5% of people over the age of 65 are getting their pneumonia vaccine. And so we're going to consider that to be a national value. And what we're curious about is comparing what's happening in Kentucky to what's happening nationally. So again, we can see in our sample that we had 63.7% actually got the pneumonia vaccine in this age group. And we can see that this is lower than that national percentage of 67.5. But the question here is, this is what's happening in our sample. So in our sample, we see that it's lower. But what's happening in the population of Kentucky of those individuals age 65 and older? And so that's what a hypothesis test allows us to do. It allows us to take this information from our sample and kind of extend that to have an idea of what's actually happening in the population. So the one sample z-test that we're going to perform here is going to say, under the null hypothesis, we're going to assume that in the state of Kentucky, we've got the national percentage, which is 67.5, and under the alternative, we're going to try to prove, is it actually less than that 67.5? So if we look back at our module 12.2 notes that we have right here, essentially what we're doing when we set up our hypotheses here is, again, we're asking that question, in the state of Kentucky, are we actually seeing less than 67.5% for the whole population based off the information from our particular sample? So we can see how to perform this test in R. So to perform this hypothesis test in R, we need to define two things. We need to define N, which is the total number of observations that we have for our variable of interest. And so our variable of interest here is that pneumonia variable that we have here. And then we also need to define the number of yeses. And so here you'll see that I've called that new pneumonia variable, and I'm looking for how many of them were equal to yes. So we can run both of these, and actually I'll go ahead and add a comment onto these. This is the total number for that. So this is the total number of observations for that variable, and this one gives me the total number of yeses. And then we can use this function. It's prop.test, and the order that we give it are k, which is the total number of yeses, n, which is the number of observations for this particular variable. P is going to be the value that we're testing against. And so here, again, nationally, we saw 0.675, and so we have 0.675 here. And then we're trying to prove whether or not what is occurring in the population of Kentucky is actually less than what's happening nationally. So you'll notice here I have the alternative set to be less. Make sure I run both lines of code. Here we go. And so here is our output from that hypothesis test. And so let's look at a couple different pieces of information that we get. So you'll notice here it lists the null probability. That is the national value that we're testing against or we're comparing to. You'll also notice that it gives a chi-squared test statistic. Now it ends up that if you perform a one sample proportion z-test, typically we write that test statistic as z, and that was the example that you saw back in the 12.2 notes. We had the statistic as being z. But it ends up that if you square that z, you get a chi-squared value. But we're going to report this as the z value. So in order to get the z value, what we need to do is take the square root of the value that we find here for the chi-squared. So here I'm just using R as a calculator. And there is the value that we get for z. So our test statistic in this case is equal to 2.42. Some other piece of information that we get here, notice it also gives us the confidence interval. But we want to be careful. If we look back up here, we can see that's different than the confidence interval that we got up here. So we don't actually want to use this confidence interval. It's actually calculating something different than what we saw earlier. And then we also have our p-value, and you'll notice the p-value is given right here. So as a reminder, when we are performing hypothesis test, a low p-value gives us evidence against the null hypothesis in favor of the alternative. So what this tells us is that in this case, we're actually able to say, hey, I've got enough evidence to show that for the whole population of people over the age of 65 in Kentucky, that I have evidence that it is less than the national average of 65.7%. So in terms of a conclusion, we could say in 2020, the proportion of adults age 65 or older in the state of Kentucky who received the, and I should say pneumonia vaccine, not flu vaccine, who received the pneumonia vaccine was less than the national percentage of 67.5%. We would give a in-text citation for that CDC link, and then we list the p-value. And so I'm actually going to look at back at the assignment again. And so in the actual assignment, I have a little bit more information about what these would look like when you add these into your report. So you'll notice here, when we get back to the assignment, I'm going to ask for which national statistic you used. So you'll copy the one from above. I'll ask for your output from R, which this will be what you highlight there. And then I also ask for your conclusion in context, and I give an example conclusion. So in 2020, the proportion of adults age 65 or older in the state of Kentucky who received the flu vaccine was less than the national percentage of 67.5%, that in-text citation for the CDC. And then usually what you see in journal articles or other information where hypothesis tests are given, it will list both the test statistic as well as the p-value. All right, so you're going to do that for both of your topic variables. You're also going to perform a chi-square test for independence. So look at that one. Let's look at that one next. For the chi-square test of independence, again, going back to the assignment directions, once you get down to the chi-square test of independence, you've been looking at comparing different demographic variables to topic variables. So here, you're going to perform 3 different chi-square tests of independence. And what you're going to do is you're going to compare, for each of those 3, one of your topic variables against one of the demographic variables. And so let's see what this looks like for the pneumonia vaccine variable. Here we're going to compare it to the education variable. So again, the first thing I'm going to do is relabel that education variable and pneumonia variable. We have seen these before when we created the contingency tables. Really this line right here with pneumonia, I don't actually have to run that one again because I already did this up above. But just for illustration here, I'm going to include both of those in case you were doing a chi-square test later on and you weren't performing this first piece. Okay. And so next thing I'm going to do is create a contingency table. So here again, we're creating a contingency table just like we've done in the past. And so here is that contingency table. So one thing that we want to be careful with is when we're performing that chi-square test for independence, if we look back at our module 12.2 notes, if we go down to that chi-square test for independence, notice here we don't have the one for two dichotomous variables. We're doing the more generic one. One of the things that we need to make sure in our assumption is that we need to make sure that we have high enough cell counts. And so if we look here at our table, we can see that we've got several cell counts are very low for the unknown education variable. And so it actually ends up that if we try to perform the chi-square test right now, we're going to end up with an error because we haven't actually met those assumptions to make this test valid. So one of the things that we can do is before performing the chi-square test, we can actually remove these unknown values, and then we'll just want to make sure that we make a note about that removal when we go to interpret our results. So I'm going to make a note right here about those unknown variables, or unknown values rather, in the code, just so I remember that I removed things. And so here we've got the unknown for education and the unknown for pneumonia vaccine. And looking at the table, I can see that across the unknown education, there were 5 people. And then looking down this way, the unknown for the pneumonia vaccine, there were actually quite a few more for the unknown for the pneumonia vaccine. So at this point, I could really make a choice here. I could either just remove the unknowns from the education variable, or I could remove both the unknowns for the pneumonia vaccine and the education variable. For illustration in this case, I'm going to actually remove the unknowns from both. But no, if you just remove the unknowns from education, your chi-square test would still be valid in this case because there are enough observations in the unknown pneumonia vaccine level. All right, so in order to remove these, again, I want to first just note how many observations I'm actually removing. So to do that, I want to add up all of these numbers for both the unknown education and the unknown pneumonia vaccine. And so to make this easy on myself, I can actually just do this down here in the console. So I've got 13 plus 31 plus 34 plus 31 plus 3 plus 1 plus 1. And so there are 114 observations. So I'm just going to make a note up here of 114 so that I remember, okay, there's 114 observations that I'm actually removing before I perform this test. So to remove the unknown values, it's actually pretty easy to do so. And we can do that when we actually relabel the values for the variables. So notice here I've repeated these 2 steps where we've relabeled education and we have relabeled pneumonia. So when we relabeled them earlier up above, notice we included all the numeric responses and then all the labels. It ends up that if you leave out one of the labels or one of the levels here and don't give it a label, R will automatically convert any value with that particular level to an unknown, or not to an unknown, but rather to a missing value. So for education, you'll notice that I've only included 1, 2, 3, and 4. I left off the 9. And then in the labels, I left off the unknown. And then for pneumonia, I've done the same thing. I've left off the 3 and I've left off the unknown. And notice instead of renaming these education new and pneumonia new, I've renamed them education no unknown and pneumonia no unknown. So that way I remember if I look at this new variable later on, oh, this is the variable I created where I set the unknowns to missing. So let's run both of those. And then I'm going to go click on my data set just to make sure that those got added in. They'll be added in all the way here at the end. So for example, notice here's the education no unknown, and here's the pneumonia no unknown. So if we scroll through here, we can actually look at some of these pneumonia or education variable values to see that it did what we wanted it to do. So I'm just going to kind of scroll through here until I see an unknown. So here's an observation where we had an unknown for the new pneumonia variable. And notice in our one that we created with no unknown, it has now been set to missing. And so that was exactly what we wanted to happen. So going back, I'm going to close this. Let's remake that contingency table. And now notice in my new contingency table, the unknowns are now gone from each. So then to perform the chi-square test, all we have to do is that table that we've created, we call chi-square.test, and we place the name of that table in the parentheses. So if we look here, we can see that our p-value is 0.5. That's a really big p-value. So in this case, it's telling me that the association was not significant. And so we might want to, kind of talk through, well, what is this test actually telling us? Well, really what we're looking for here is whether or not there is an association or whether or not these things are independent. So let's talk about what this is actually telling us. So when we perform this chi-square test for independent, what we're doing is we're assuming that the two are independent, and we're trying to prove whether or not the two are dependent, or in other words, there's some association. So in the context here, what we're saying is, does whether or not someone gets a pneumonia vaccine vary based on education level? So that's what we're trying to figure out here, and that's what the chi-square test allows us to do. It takes that information from the sample, and it says, hey, is there enough information in this sample to actually prove whether or not someone gets a pneumonia vaccine depends on, or is associated with, I should say, their education level. And so if you'll recall, we've looked previously at contingency tables, and we also look at that standardized bar plot where we actually compared education with pneumonia vaccine. And so if we pull up that document, remember that this was the bar chart that we saw previously. So here for this chi-square test, we're not considering the unknown because, again, the levels here were really small, and we're also not considering the unknown below. So we're really just comparing these 3 yellow bars, or 4 yellow bars, and these 4 red bars. And as we look across here, notice that these percentages are fairly close to one another. There's not a huge difference in terms of the percentage that are not getting the pneumonia vaccine compared to those that are across them. Now we did notice that there was a slight increase, but that difference was at most 3%, so it was very, very slight. And so what this chi-square test tells us is even though we saw those slight differences in the sample, we actually don't have enough information in the sample to say, yes, in the population, there is a significant association between pneumonia vaccine compliance and education. And so that's what this chi-square test does for us. And so here we can say the association between education and pneumonia vaccine compliance in the state of Kentucky was found to be non-significant. And the p-value here again is 0.55. Now we do also want to make a note that for the chi-square test of independence, the unknown responses were removed from the data set. So that way if someone were to replicate what we're doing, they would be able to say, oh, okay, I know I need to remove those unknowns. And again, it makes sense to do that in this case because the counts for those unknowns were fairly low, and so they would have violated our chi-squared assumptions that we would need. So now going back to the actual assignment here, I also have that example write-up as well under the chi-square test. The difference here is, notice here in this write-up, I did include the chi-square test statistic as well as the degrees of freedom. And so typically in write-ups, you will see the chi-square test statistic, you'll see the degrees of freedom, as well as the p-value. And typically when we see the p-value written in documents, you will see them written as a capital P that has been italicized. And so that's another common way that you see those written. So when you write up your conclusions for your 3 chi-square tests for independence, you'll want to write up your conclusions very similar to this. All right, so that was kind of an overview of how to perform these two different chi-square tests using the data from the state of Kentucky. So now what I want to do is just kind of walk through how you're going to complete this assignment for your state. So first of all, located on Canvas, you will find the R script for you to fill in. So as always, the first thing we're going to fill in here is just how to read in your data. So you can copy this from any of your previous assignments where you read in the data. I'm going to copy over this piece. Next, you're going to complete two different one sample proportion z-tests. And again, you're going to do this for your two different topic variables. So for example, if you were working with the pneumonia vaccine, or whichever one you're working with really, you could go ahead and copy over this piece of code that I have here. And then what you'll want to do is start out by making a comment right here about which of the two variables you're going to be working with. And so, if you're working with breast and cervical cancer, you might say, hey, this one we're going to work with the mammogram variable, and then on the next one you'll look at the pap test variable. So you just want to make sure change this comment to which of the variables you're working with. You do want to make sure you include that library tidyverse. You only need to include that in one of the spaces. You don't need to include it in all of them. Next line of code, what you'll want to change here is you'll want to have the data set for your state, create a new topic variable, change your data set, and then again, put in the variable that you're working in from the data set and change your levels and your labels. You can copy this directly over from previous code that you have had. You should have already done this line of code for both of your topic variables in previous assignments. Next, you're going to create the table that has, we'll go ahead and run this so we can see what it looks like. You're creating the table that has the count and the relative frequency as well as the confidence interval for this new variable that you created. This comes directly from the Module 11 assignment, so you're probably going to be able to copy this code again directly over from your Module 11. But in terms of pieces that you need to change, you want to have the data set for your state, the new topic variable you created with labels. The new topic variable you created with labels also goes here, and then you don't need to change anything else in this code to produce this table. So you're only changing those three things. Next, you're going to go through and perform the actual hypothesis test. So to perform this hypothesis test, what we're doing is, again, we're looking at the total number of observations for the variable as well as the total number of yeses. And so to change this line of code, you'll just want to enter in the name of your data set, and then again, the new topic variable you created. And then for the total number of yeses, you'll put in your data set, and again, the new topic variable you're working with. Be very careful because R is case sensitive. So for example, if up here in your labels for your variable, you used a lowercase y or you wrote this slightly differently, you will have to change the yes that is here. Other than that, no changes are needed. So you could run that. And then to run the prop test, the only thing you'll need to change are two pieces here. You'll want to change this value to be the national statistic that you are comparing to. And then the alternative will depend on whether or not your observed value in your sample was less than or greater than the national statistic. So in this case, the value that I observed for the state of Kentucky was 63.7%. That's obviously less than 67.5%, so I chose the less than. On the other hand, if I had observed something in my sample that was greater than, I would want to do a hypothesis test to see if the population of Kentucky, the percentage was greater than that national average. You would change this less to be greater. And you can actually read more about the prop test by doing prop.test. And you'll notice here it actually tells you what those different options are for the alternative. And so you can see the greater. You can also do what's called a two-sided test. So in a two-sided test, you would be testing whether or not to see in your population for your state, the value that you found differs from the national average or the national percentage. And then don't forget that the way that R reports these particular hypothesis tests, it does it with the chi-square statistic instead of the z statistic. There's nothing wrong with the chi-square test statistic here. It's just more commonly you see this written in the form of the z. So we do want to take the square root of that test statistic there just to be able to write that in the form of z for your report. Now, one thing that I didn't point out earlier, which I think is really informative, if we think about what it is we're trying to do with this particular hypothesis test, is we're trying to prove in the state of Kentucky, is the value less than, again, 67.5%, the national percentage? Well, recall that confidence intervals give us a range of reasonable values for the parameter or what's happening in the population. So if we look here at the confidence interval that we found for the proportion of yeses, notice that this entire confidence interval falls below 67.5%. In other words, our range of reasonable values for what's happening in the population of Kentucky falls completely below that national percentage. So before I ever ran this hypothesis test, I actually knew that it was going to be significant because the confidence interval tells me what all of those plausible or reasonable values are for the parameter. So this just even further supports what it is that we found. So then when you go to do your second one sample proportion z-test, you'll do the exact same process. You'll just do it for your second topic variable. And then again, you're going to do 3 different chi-square tests of independence. So to do these, again, you can come over here and copy this code. This one does look a little bit longer, but again, majority of this code we have seen before. Start out by relabeling our variables to give it the meaningful labels. We create the contingency table. Now, when you create the contingency table for your particular variables, where you're comparing your demographics to your, to your topic variables, if your counts here for your unknowns are not low, like they are in this example, then you can actually go ahead and run the chi-square test just using this contingency table. The only reason we remove the unknowns in this example is because the cell counts are low, so we're violating some of the chi-square test assumptions. And one thing just to show you what this looks like, so let's say I ran that chi-square test, but I ran it on this table here. Notice that it actually gives me a warning that says the chi-square approximation may be incorrect. And again, because up here, I'm running that chi-square test on this table right here, where, again, I know that I don't have the cell counts that I need. But in your data set, if you've got high enough cell counts, then you don't have to remove the unknowns. So if you need to remove the unknowns, continue with the next part where you redo the labeling and recreate the table now that it has the unknowns removed. Again, very similar to what we've done before in terms of relabeling the variables. Nothing too new here other than if you want to remove the unknowns, just leave those values off. Recreate your contingency table. Again, we've seen this in the past. We've done this several times. So really, when we look at this chi-square test, this piece right here is the only new piece of code that we have, because we performed the chi-square test on that contingency table that we have seen in the past. And then just as a reminder, in the assignment, I have examples of what each of these conclusions should look like for the 5 different hypothesis tests that you perform. Now, I will say when you get to the next draft of your report, for each of the comparisons that you had in the third part of the body of the report, you're going to include one of these chi-square tests. So if you can't work with your group members on these assignments, but if you do want to send them a quick communication and say, hey, I'm doing this comparison, or I'm doing these 3 comparisons, do you want to do a different 3? Feel free to do that. You just can't work on the assignments together. But that way, when you go to work on the next iteration or the next draft of the report, you'll already have all of these chi-square tests performed. So as always, if you have any questions, if there's anything that I can help with, please let me know. I'm more than happy to help with anything that I can. So please just let me know.